GSIs that I should reserve some minutes in the beginning?
No, I don't think so. Nothing comes to my mind.
Okay. One announcement maybe from my side. I had office hours today, as advertised before, at 1 p.m. But going forward, starting next week, that will move into a different slot on Tuesdays, and the website is updated to reflect that, and the appointment slots are updated for subsequent weeks. This is to avoid a triple booking on that wonderful slot going forward. And for those students who, there was 6 or 7 concurrent enrollment applicants that submitted their applications a couple weeks ago, and they should be on track to get approved, and you will be added to B courses, and a group will be formed for you. And since you have started late, you might you'll get a couple extra days for finishing homework 1. But welcome to CS267, and we're not admitting any more students beyond this point. And it's another announcement. If you just looked online and saw CS267 and decide to join the class, it's too late. But if you've been here and you have a group, you're studying homeworks, don't worry about it. You're in. So today we're going to be talking about shared memory programming, and I'll spend a majority of my time talking about OpenMP, which is one of the concurrency platforms that allow you to write efficient code for shared memory architectures. And just to recap, a parallel architecture, you can abstract it away in something that looks like this. There's several processors. They can be grouped in different ways. And there's memory. They can be grouped or distributed. And there's usually a network, some sort of network that allows the processors to go to the memory. And that's essentially the most abstract way you can think of it. And various answers about what the interconnect is and how it's connected will determine what kind of programming environment we're dealing with. And this is probably a slide you have seen in the long history of parallel languages and machines, vector machines, the kind of machines that were basically designed to get instruction level parallelism that used to be the king in early days. And then SIMD machines, single instruction, multiple data machines, became ruling the interface. That was kind of hard for lots of irregular problems, except for a few where people were able to invent ingenious methods to handle those. Then shared memory processors came. This is simply a history that tells you that things repeat over time, and likely to many things that were popular and no longer relevant will come back. You can argue that a lot of vector machines didn't come back in pure form, but the kind of way we programming GPUs are arguably vector machines, for instance, and seems to be where we are. And as you know, in this class, you'll see pretty much all the categories. But let's get to essentially our important part of today's lecture, shared memory multiprocessors. Today, the kind of machines, even the distributed machines you're programming, are based on large shared memory machines connected to an interconnect. So you'll have to learn how to efficiently program shared memory multiprocessors, even if you're operating in a distributed memory environment, simply because treating each one of these cores in a machine as if it's a distinct entity is usually not the best way to program them in terms of memory consumption and scalability. So today it's going to really look like we're going to first go over a little bit over threads, which is going to be very brief, and then we'll dive quickly into OpenMP as our concurrency platform. And I will be introducing several important concepts along the way, as opposed to introducing first and then using them in examples. So the things like cache coherence will come as the example shows its importance. So what is a shared memory architecture? It's simply the initial picture you saw in slide 2, where the memory is, you can think of this as a monolithic block. And there's various processors that are able to reach to this memory block directly. And anything that is updated in the shared memory location simply should be technically visible to the other processors. So everyone has access to things that are sitting in the shared memory. And usually each processor has its own private memory in some form, and that is allowed by the programming environment. Most programming concurrency platforms that allow you to write shared memory programs allow you to declare private variables that are not accessible by the other processors, even though technically any memory of a single machine is accessible from other threads. The programming environment disallows this. And how the threads communicate, they can communicate either implicitly by writing or reading the same shared variable, or they can coordinate by explicit synchronization calls. And we'll go over many of those. Threads used to be how people program these things for many, many years, decades, and still many concurrency platforms under the covers convert your program into some sort of threading environment. And there's different threading standards. We're going to go over the POSIX one, which is probably one of the most heavyweight ones, but the most commonly implemented one. So the POSIX simply stands for the POSIX threading. pthread stands for POSIX threading interface, and POSIX stands for Portable Operating System Interface. So this should run on any Unix-based platform, right? And that allows you to create parallelism, synchronize threads, but all communication is essentially implicit through writing through shared variables. And the syntax looks like this. I'm going to confess somewhat of an ugly mess because of its generality. And so the third, when you create a thread, you have to pass a function pointer of the function that is going to be executing on that thread. And that's a really long, ugly third signature of the third parameter, there, thread function. And then you define the thread ID that will be returned to you so that you can get a handle of what the thread that's been created, various attributes, and of course, all the arguments to the function. This looks really abstract, but once you see an example, it's actually fairly simple. Here you have a function that says hello, and then you can create 16 threads and pass the say hello function to it. And as you can see, each one of these threads are returned to one of the elements in the thread array. And then once you join them, essentially they start executing. They have to finish executing once you join them. So this needs to be compiled with the pthread library. Some of the compiler wrappers will do it for you automatically, but not always. So here's one way, the most common way parallelism is extracted in scientific programs, which is you have loops over lots of variables. And this looks like your homework too, where you're updating cells. Doing this in pthreads would mean that you would have the most intuitive way you can think of would be to have your for loops, and inside your for loops, you would be creating threads for the updating the cell function. Now, that looks easy to program, but it's certainly not going to be particularly fast. And here's the fundamental reason why, because each one of these cell updates are very cheap, and creating a thread is usually an expensive activity. You could write your function such that each function executes a certain iteration space of the for loop. For example, it only iterates over 100 times. And you can tune that parameter. You say, okay, this chunk size is large enough that it amortizes the cost of creating this function thread. But that needs to be done manually. So that is fundamentally why pthread programming gives you a lot of control, but it's also painful, so to speak, to implement. It doesn't do many things for you automatically. And so here's the other issue with writing explicit operations with threads. Suppose you have a shared variable, which is S in this example, and you are simply doing a reduction. You're computing a function over elements of an array A, and and adding the returned value that's from that function to a common element S. Now, this is one fundamental, very simple way of creating a race, so-called a race condition, because two threads are updating the same variable. A race condition is happens when multiple processors access the same variable, and at least one of them is writing to it. And in this example, both of them are writing, but even if one of them was writing and one of them was reading, that would still be a race condition. So how do you avoid that in pthreads is this, you might have seen this in your operating systems class if you've taken it, is it's called a mutex, mutual exclusion. You can get a lock, acquire the lock, access the data, update it, and release it, which means that only one processor will only access that portion of the code between the acquire and release portions of your code. So that will guarantee correctness, but there's several issues with that. Obviously, we're going to go over that. And there's generalizations of mutexes called semaphores, which allow more than two threads to simultaneously access those. It's think of them as mutexes as binary and semaphores as k-array objects that allow synchronization across a larger group of processors. And frankly, the code looks like the following. You, of course, have to add your threading headers and initialize your mutex, lock, unlock it, and destroy. So things you have to remember is if you forget to destroy these mutexes, they consume a lot of space, and eventually most programs will run out of available mutexes. And the other issue you will have to worry about is if you're creating a deadlock. And in this example is the simplest way of creating a deadlock when two threads are locked in a different order. In this example, what you're seeing is thread 1 acquired a lock on A, thread 2 acquired a lock on B. So thread 1 is waiting to be able to get the lock to B. Of course, that's held by thread 2 and vice versa. So each one of them are waiting for each other's lock, and that is the canonical example of a deadlock, which can be avoided in this simple case by having all threads lock in the same order. While that's easier said than done, in simple examples like this, it's a trivial solution, but in really complex problems, it might not be all that feasible. So recognizing deadlocks, resolving them are really hard, and they're hard to reproduce sometimes when the program is sufficiently complicated. So I think where I'm trying to get this at is pthreads allow you to write very complex shared memory programs, but it comes with many pitfalls that create lots of bugs that are hard to resolve, hard to reproduce, even though lots of debugging tools have been developed over the years to find those bugs and resolve them. So that's why people have been developing concurrency, so-called concurrency platforms that does the threading somewhat not that explicitly to the programmer. And I think this is exactly what I said one slide early. The other issue with pthreads, which is not generally with threads, is pthreads is supposed to run in every Unix environment, which with generality usually comes with overheads. So people who have worked on this area eventually learn that pthread creation is sufficiently expensive that it makes sense to write lightweight threading libraries. And there's various libraries like that. One of those that come to my mind is qthreads from Sandia, but other things. And finally, the issue probably more prevalent is the parallelism you express in pthreads is in some sense more imperative than all the concurrency platforms. You say, create this thread, and the pthread has no option. It will create that thread. Whereas in many concurrency platforms, what's going to happen is it's usually a suggestion. And if the runtime decides that it's not worth parallelizing that part of the loop or that function, it will silently ignore you because the program is still correct so that it doesn't overwhelm the resources. So what is OpenMP? This is a as I said, it simplifies shared memory parallel programming. It's an open standard, which is nice compared to a lot of other things we have to deal with, like Intel threading building blocks or NVIDIA's CUDA. This OpenMP is compiler directives. So it's a bunch of pragmas that you're annotating your C, Fortran, or C++ code. It has very few library calls and environmental variables. Most of it is really about preprocessor directives. It has been grown pretty substantially over the years. It's now in, I might be old here when I say 5.0. I think right now we are in 5.5 or something like that. But you don't really need to know more than 5% of OpenMP to write good parallel programs. And I believe we're going to cover essentially everything you need today to write efficient OpenMP programs. So what is it going to do? It will allow a programmer to separate its program into serial regions and parallel regions, then to think about always executing threads. So it's easier on the programmers, and you can choose to only incrementally parallelize your expensive parts of the program with loops, and then don't touch the rest and let the rest of it become serial. But of course, you have already learned about Amdahl's law, which will prove that for any program, if you have substantial serial regions left, it will eventually dominate the runtime. So don't forget that. What OpenMP will also do is it will also provide you much better synchronization constructs like barriers, so you don't need to implicitly synchronize threads. You can do it more explicitly, and and many times it will actually synchronize automatically for you when you use these compiler directives. What it's not going to do is, of course, it's not going to parallelize things automatically for you. This is not some sort of compiler. You give the serial code and it returns you the parallel version. You have to do many things still yourself, and it gives you more control than some other concurrency platforms, for example, like Silk, which we won't talk about, but we will mention at the end. And you can still have data races. It really depends on how you write the program. As I said, it's been growing somewhat substantially. I saw that in order to not lose resolution, I didn't plot the number of pages for the latest version, which is 666 pages. So it's an ominous number. I hope they have a different number for 5.5 or whatever the latest release is, but it's getting more complex. However, really the stuff you need is not that long, as I said. The common course that we're touching here is about creating parallel regions, annotating loops so that they execute parallel, reducing over a variable, scheduling constructs, and how the variables inside parallel regions are initialized and shared across processes. These are the private, first private, shared, and this is essentially all the things that we're going to go over today. In case you want to know what's happening under the hoods, really OpenMP is essentially a runtime, right? The compiler understands OpenMP and is able to compile your code with OpenMP. Most compilers are good with this. Intel compiler, GCC. Clang had always OpenMP problems. I don't know, I haven't checked it this year. And every time I got a new Mac, I would have to change my default compiler from Clang to GCC in order to get OpenMP. Hopefully this is changing because I don't know of any other popular compiler that doesn't have OpenMP support. And really, this is this stack that kind of looks like. It's mostly repetition. Let's get into a real example so that I don't bore you with concepts too much. Let's say you have a program that wants to print hello world. And this is the serial version. What if I want to print hello world, but from each thread that is available? And all I have to do is to add the header for OMP and create a region, OMP parallel. And you need to compile this thing with these FOpenMP for GCC and various other options for Intel and Portland group compilers. And if these have changed, please email me. GCC and ICC hasn't changed, I know, because I tried yesterday. The other ones, I didn't. So let's go a little more deeper. What's happening here is when the compiler sees Pragma OMP parallel, a number of threads start executing this concurrently. So many hello words will print out. So what kind of output do you expect? So this is not a actual in-person class, but you would expect several hello words printed, depending on how many threads you have. And for many reasons, this is not going to be a hello word clean, because threads can interleave in time in a different ways. So you might see something like this: hello, hello word, hello word, and that's normal. And because we haven't provided any synchronization across processes within that region, they're going to chaotically execute that code inside the parallel region. Really, the programming model for that reason looks like the following. You have serial code when there is no pragmas, a single thread is executing. And as soon as we call OMP parallel, a region starts that is executed by all the available threads. And this number might depend on the implementation and the resources available at the time. And then once that parallel region is closed, then we're back to the serial portion. And this is going to happen for the next parallel region and so on. And the little detail here is you can create parallel regions within parallel regions, and that's called nested parallelism. And I'll describe this to you, but I want to say it here. If you try to create nested parallelism, you might, and you don't get it for some reason. It might be because your environmental variables are different. The default ones might be disallowing it. And I will show you how to actually allow nested parallelism. These are controlled by OpenMP environmental variables, and many compilers and runtimes turn it off by default. So as we shown in the hello world example, you create threads in OpenMP with the parallel construct, and you can actually get the thread ID, which is nice because it's not some sort of random process ID you get from Python multiprocessing library. You get something that is numbered from 0 to maximum number of threads -1. So you'll get, if you want 4 threads, you can set the number of threads before you start your parallel region, or you can actually have it right by your pragma. You can say pragma OMP parallel num threads 4, which is effectively has the same effect as setting the number of threads before the loop. So when you set it in the pragma, it will set it only for that parallel region. If you set it before, it is trying to set it for the whole program until you unset it. And you're going to get the thread numbers from 0 to 3 in this example, because I used 4. So what does it kind of look like in the execution? That is map this back to the fork join parallelism pictures. The proof function will be called by different IDs, 1 for each thread. And it will be called 4 times with different variables like this. And once the parallel region is out, the threads will join and they will be distracted. At least virtually they'll be distracted if OpenMP runtime is smart and decide that creating threads and distracting them is expensive. It may choose to keep those threads alive and let them live on a thread pool inactive. So that's kind of one of the differences between pthreads and OpenMP. When you create threads in pthreads, they are created, and when you join them, they're finished and they're distracted when you call the destroy threads. However, in OpenMP, once the loop closes, virtually all the threads disappear. The actual operating system thread might still be alive. It's just the OpenMP might decide to keep them alive so that it doesn't have to recreate them, which is an expensive call. So it will reuse from the pool. It's really implementation dependent. So a couple of things you might want to know is just because I set the number of threads to 4, there is no guarantee that's going to be the case. So it's always good to check. Implementations are allowed to use fewer threads than you ask them for. So as far as I know, they cannot give you more threads than you ask for. So get the number of threads inside the region. A guarantee is once a team of threads is established, it's not going to silently reduce. So you can actually rely on the number of threads that you get inside the parallel region. If it says 4 here indeed, then later within the same parallel region, it's not going to become 3. But just because you said 4 doesn't mean there's actually going to be 4 real threads. And this is a potential bug in programs. Even though your code might run in your local machine, if the runtime is different in a machine that you're porting your code and it's implementing it differently, you might find yourself in trouble. And this is a bug I actually was dealing with yesterday. So know the spec that the number of threads that you ask is not exactly what the OpenMP runtime has to give you. In many implementations it does, but sometimes it can give you fever. All good. So let's go over an example. This is computing pi. This is the same example we're going to see in distributed memory programming as well. And if you remember calculus, you can compute pi by integration, right? So, and how do I approximate that? Well, by summing the area of little rectangles. And the smaller the rectangle is, meaning the narrower its width, the better I approximate. So I'm gonna basically approximate pi by using these little rectangles, and the number of rectangles is going to be defined by the number of steps. So the more steps I have, the better I approximate. So in this example, I have 100,000 little rectangles that I'm using to approximate pi. So and I sum the area of I get the cumulative sum of all the areas of the rectangles, and I calculate pi using that. So this is the serial code, fairly simple, but this is a very good candidate for parallelization. Why? Because there's a loop and it's executes many times. It's sufficiently expensive. So why don't I parallelize with OpenMP? Great idea. And how can I do that? So right now, nothing is parallel. All I did was just put a bunch of timers so that I can see how long it's going to take. So far, all I did use from OpenMP is to get the timer functionality. There's no parallel region yet. But I want to open up a parenthesis before I explain what might happen in reality, which is something about memory consistency. So when we say shared memory architectures, and when we say you can read and write through shared variables, the question becomes, well, but what about caches? Many processors you have, or effectively all processors have caches for performance reasons. And usually there is a private cache per core or per processing unit, per processing element. I think I have lost track of the marketing name for those, but there's a cache. So that is somewhat of, has a local copy of a portion of the memory. And how frequently that is updated and under what rules are updated are processor dependent. And it's usually kept somewhat, let me get this water. The programmer doesn't need to usually know those details. But what's going to happen when you program for shared memory, you'll have to think about the caches for one particular reason. So what happens, let's say I update a variable that was in my cache. Does that suddenly become available to all the other threads, or is it only locally available to me? So that is the difference between a write-back cache and a write-through cache. And write-back cache only updates the data in the main memory when the variable when the variable is evicted from the cache of the private cache of the processor. And write-through always updates the main memory whenever there's a write. So you can see that there's write-through is easier to program in terms of, in some sense, it's easier to make sure that the caches are coherent, because whenever one processor updates a cache, then the value on the main memory is updated immediately. But the downside is it's sufficiently expensive because many of the operations are actually writes to the memory. So that's going to create a lot of memory traffic every time. And it might essentially defeat the whole purpose of having a cache. Every time you have a write, then you have to actually create traffic to the main memory. That might completely eliminate the advantages of the cache. And write back caches has other issues that, and then I think I'm going to show it in an example. Let's say there's a memory location U, processor 1 gets it into its cache, and processor 3 also gets it in the cache. And what's going to happen is processor 3 is going to write 7 to U. And if this is not a write-through cache, that is not immediately updated in the memory. And now, what does processor 1 read at that point, right? So as you can see, there's issues. If this was a write-back cache, you have somewhat big issues because the main memory value is different. But even if this was a write-through cache, remember, you still have an issue. If P3 updated this value and the write-through cache immediately changed the main memory value to 7, P1 still has the data in his cache and thinks it's 5. So even with the write-through cache, it still sees 5 unless there's a protocol that ensures that it gets the refreshed value from the main memory. And these protocols, there's variants of this, and you're going to see it. You can see it in other classes in architectures. These are called cache coherency protocols. We're not going to cover them here, but I'm just bringing that reality. And this is essentially the summary of what I said, so that when you see the example with OpenMP, you understand what's happening. So what is the granularity of a cache line? It's usually, again, processor dependent, but you can think of it as either 64 or 128 bytes, as far as I remember. So when you get some variable into your cache, the nearby words also come. And that will actually explain some of the strange performance we might see in our example later. And finally, this is showing you a pitfall of shared memory architectures, because something in the background has to constantly keep track of the correct values of things that are in individual caches. Its scalability usually is limited, somewhere around 100 processors. And this might change, but fundamentally, it's a really hard problem to scale cache coherence to thousands of cores, and that might be the limiting factor in terms of shared memory parallelism, and not the silicon or any other issue. Okay, I'm not going to talk about the Snoopy protocol. This is a very common protocol of how to keep caches coherent, but it's the subject of another class. Instead, what I want to do is go back to our example and see what's going to happen. The parallel pi program. So I parallelize this program by putting a pragma OMP parallel, and I get the thread numbers within that region, and I manually divide the iteration space that was from 0 to number of steps in across threads. So how do I do that? Well, I say, okay, thread 1 gets the iterations 0, T, 2T, 4T, where T is the number of threads. And thread 2 gets the iterations 1, T plus 1, 2T plus 1. So that's how I divide it. I could have divided blockwise. So essentially what I did was a division that is known as a cyclic distribution of work. This seems all nice, and what do I see when I run this thing on my previous laptop? Well, I don't see all that great scaling. It's not maybe bad, but it seems like I could have done better. And then I opened my new laptop, which is what I'm using right now. Things are actually somewhat better here. Things are I think scaling better. So, but what might be the issue here is there's different cache coherence protocols, and you might want to ask yourself, okay, what does it have to do with the caches? Now, imagine look how I'm setting these sum variables, because there used to be a single sum variable, and I don't want to create a race condition on writing on it. Instead, what I did here is I created an array of length number of threads, like a length 4, and each thread is updating a different location on that array. So thread 0 is updating sum 0, thread 1 is updating sum 1, and I think that everything is great because there are no conflicts, right? There is no data races, and all I need to do is to just go over and sum the elements in that array, which is really short, and this can be done serially. It doesn't need to be parallelized. However, as I said, there is the reality that cache lines include multiple elements, because a cache line is 64 to 128 bytes. That means many adjacent words are in the same cache line. So what might be happening, in fact, what is exactly happening in our example is the sum array is fitting into the same cache line because it's very short. Sum 0, sum 1, sum 2, and sum 3 are all in the same cache line, and the 0 thread pulls sum 0, and of course sum 1, sum 2, sum 3 all together go to the private cache of core 0. Same thing happens to the private cache of core 1 and core 2, and so on. Well, every time we update sum 0, sum 1 by different threads, the cache coherence protocols looks at it that says, okay, this cache line is in the caches of every single processor. So since it's updated, I have to somehow propagate that update to the other processors so they don't get the wrong result. What the cache coherence protocol doesn't know is it's actually the processors are updating different portions of that cache line, and they're essentially not sharing any real value, semantically speaking. They're only sharing cache lines. But processors cannot know that fact because they don't have access to the semantics. So they're just invalidating individual cache lines at every update, and that gets really expensive. So what can I do to solve this problem? Well, I can try to ensure that different variables that I'm updating sit on different cache lines. So let's say I looked at my processor specifications and I noticed that a cache line in the L1 cache is, which is the private one, in this case, is 64 bytes. So that means I'm going to pad it with 8 because this is a double variable. The sum is a double variable. And I'm going to ensure that sum 0 is one cache line apart from sum 1. And I'm just going to update it this way. So I'm wasting a little bit of space, but remember, this is tiny. And what happens is I'm much better off in terms of performance, at least on my old laptop, by a factor of 2. Or you can say this is actually probably going to scale much better because, again, I have only a 4-thread machine. The cache coherence protocols struggle when there's a lot of threads. So even here, there's a noticeable difference. Now you can argue why the difference you see is much smaller in your modern laptop. As I said, cache coherence protocols are processor dependent. And it seems to me that the newer Mac I have has a better cache coherence protocol. That's all I can argue at this point. Just know that false sharing exists, and this is one way to avoid it. But you can always say this looks ugly. I don't want to know the L1 cache size, and I don't want to know how long it is, and I don't want to pad it the way you did it. Can you tell me something better? Well, of course, I'll tell you at least two more ways of solving the same issue. Let's talk about synchronization. So you can, as I said, OpenMP allows you to synchronize across threads with explicit calls. And two of the most common ones are critical and barrier. And critical says there is this region that only one thread should be entering at once. That's the critical region. That's also a term you might have seen in your operating systems class. Everybody will execute that line. That line is not going to be skipped, but it's like a locked region in some sense. Only one thread will ever enter that region at the same time. Okay, what about the other synchronization thing? It's the barrier. I want to talk about it before I start using this thing. A barrier says all the threads must reach to this line before any other thread can move past it. So it's, as you might expect, it's everybody needs to come to that line. The name, to me, I think maybe too ingrained. It feels natural. If it's not, let me know. So, for example, why do I need a barrier in this example? So what's going on? I create a parallel region, and I do some expensive calculation, and I update some array. Every thread updates a different portion of the array. Yes, there's false sharing, but that's okay in this example, actually, because remember, this is only going to execute once. If all your if your false sharing happens once in a blue moon, that's not going to create enough traffic to burden you. But if you have been if I was updating array within a tight loop, 100,000 times, that would create a lot of traffic. Here, there's only one update. But then what's happening in the next calculation is potentially other threads are using this array. I don't know what's happening inside this really big and ugly function, but assume that the big and ugly accesses all of the array, not just the particular ID that thread is updated, but is potentially the other indices of the array. Well, that means the other threads should also finish what they're doing with array before I can call really big and ugly. So that's why I insert a barrier. All right, so let's use this critical concept to get the sum of our rectangles in a way that doesn't require padding. So for that, what I'm going to do is I'm going to create sum as a variable inside my parallel region. So sum used to be outside my parallel region, which essentially makes it a shared variable. And I'm going to go deeper into shared variables in a couple of slides. But for now, let's just say that if it's inside a parallel region, that variable is private, and every thread gets its own copy. So every thread has its own copy of the sum variable, following the typical scoping rules of programming languages, and they update it independently. Now, I need a critical region where I'm getting the sum and updating pi. And I have to do it here because sum is inside this OMP parallel region. And if I don't use it when this region goes out of scope, well, I'm going to lose sum. I have to actually use that value and update the pi before it goes out of scope. And I do that by updating pi. So this is a really smart way of doing it. Because the alternative bad way of doing it would be to write a critical region, right? A naive way to do it is write a critical region here right before I update the sum. Instead of having sum as a private variable, I could have moved it outside and put a critical so that everybody would be essentially updating sum in a locked way, in a safe way. That would be safe. That would give you the correct result. However, because I'm serializing the computation in that update, which is an expensive operation, for every single rectangle, I would effectively see no performance speed up. Here, by using a local variable and doing all my updates to the local variable, and then writing to the pi only once after that loop is executed, I'm avoiding that serialization issue to a larger degree. And since I have no arrays, I have no fault sharing, and this looks nicer, and I get effectively the same performance as the padding, which you can argue that is a cleaner solution. Now, one thing that I don't like about this example is I manually decide how these threads are dividing the for loop. And in some sense, I am actually assuming a couple of things. And one of those things is that the number of threads is dividing the number of steps evenly. And I don't even know if this might actually correctly run, even if it doesn't run, but it's my job to divide the number of steps to the threads here, which is something I don't like. Now, of course, can I get around this? Okay, OpenMP developers like simplicity, and they did. So there's this concept called a loop work sharing construct. This doesn't create a parallel region. This divides the work among processors. So you say, okay, I'm creating an OpenMP parallel region. And once I put OMP parallel for, it says, divide the work of this for loop across the threads. Remember, if I didn't put the for here, every thread would execute n times. Now that I put the OMP for, pragma OMP for, now every thread will only execute n over t times. And it will be up to the OpenMP to divide the iteration space to processors. And that's going to simplify my code. And here's what it kind of looks like difference. In one case, I'm manually deciding what each thread is going to execute within the loop. In the other example, I just write it in one-liner or MP4 and let the OpenMP runtime divide it for me. Well, even this one looks a little long, right? So I write OMP parallel, then I write for, and you'll be surprised how many experienced programmers actually make mistakes and bugs with the OMP for, because this is a work sharing construct versus a parallelism construct. So how can I combine the parallelism and work sharing constructs? There's a shortcut name, which is just a syntactic sugar. These are equivalent. Instead of creating a parallel region and then writing a work sharing construct OMP4, you can combine these things, which is called pragma OMP parallel for, and that will essentially say, execute this for loop in parallel while dividing the work across processors. Okay, so far I have ignored, or at least didn't touch on how that work is divided into processors. And in the example, pi example you saw, it's kind of easy, meaning every rectangle calculation is effectively taking the same amount of time, assuming each floating point multiply is taking the same amount of time. So if I just statically divide the calculation of each rectangle to threads, I get a load balance execution. What if that's not the case? What if I have an iteration space where each execution of the loop takes a variable amount of time? Well, OpenMP has a solution for that, which is to use dynamic scheduling. And basically here, what you say is, I don't know what each iteration of the loop is going to take. It might be load imbalanced. So why don't you dynamically execute this? In the static, OpenMP will look at the iteration space. If it sees 1,000,000, it will divide it to T processors somewhat equally. And how each chunk is going to be determined is there's a default value. You can actually tell exactly what's the chunk sizes as an annotation to the pragma, and you control it if you care. In the dynamic, you say don't statically divide it, and there is a chance that things are going to be really load imbalanced. So start executing some, and if one processor is burdened, please let some other processor take its job, its tasks. And that is actually very successful if you have many small variable length jobs. inside your loop or inside anything that you're scheduling. However, imagine you have highly variable but few jobs. Let's say I have 10 threads and I have 10 iterations of this very loop, and even though each iteration is expensive, meaning I'm not really worried about thread creation, some iterations are taking 10 times longer than the others. Well, remember, if my jobs are that big and I have only 10 iterations and 10 threads, there is no way that the dynamic would do anything good for me, because there's just not enough ways to bucket these things into equally sized things, even if it was using dynamic execution. So dynamic works where when you have sufficiently many small variable length tasks. Maybe small is not the right word to use. You just need to have enough tasks that's more than the number of threads that you're trying to parallelize, so that it can bin pack them in a nice way. So let's go to a real example that I had the pleasure to implement last night, which is, let's say you're doing a block matrix multiply that looks very similar to the things that Kathy has been talking about. And it looks somewhat what you're going to be doing in homework 1 anyway. But however, the matrices are sparse, meaning there's a lot of zeros. So they're represented as a sparse format. I'm not going to talk about that. But each sparse matrix multiply will take a variable length of time. So this is not the case for dense matrix multiply. If you have the same block size, usually it takes the same time. So here it's unpredictable, and you don't have a good sense of how long each call these I annotated with SPGem are going to take. But so I write this loop, which is a triple nested loop over blocks. These are not individual elements. And the innermost kernel SPGem is basically executing B to the 3 times, as following the cubic matrix multiply in block form. So B is small, think of it as 10. Of course, the first thing I can do is I can put an OMP parallel 4 on top. Well, that's clearly not enough parallelism, because it's only parallelizing the first loop, which is only 10. And if I have 8 threads, which is like my laptop, I don't think I'll find enough parallelism, and not, especially not if things are load imbalance. So here's a really nice way of fixing this problem without trying to collapse these loops manually. You can collapse these loops manually into a single big loop and write OMP parallel 4. But OpenMP will do it for you, which is something I really like, syntactic sugar. What this says is parallelize the first 2 loops in a collapse way. This is really different than putting 2 OMP parallels nested in each other, because if you nested them, at that point, the OMP runtime is actually individually parallelizing them. Here you're saying, think of this iteration space is going from 1 to B squared, and divide it like you would divide an iteration that goes from 1 to B squared, as opposed to 2 iteration spaces that are going in length B. And it will do that. However, when I benchmark this thing, I still see questionable runtime scaling, the single thread runtime and the 8-thread runtime. It's a factor of, it's hard to say, it's only, I would say, a factor of 1.7 faster, which is not all that impressive. How about I used what I just learned, dynamic, and I just put one scheduled dynamic down there. And what do I get is almost twice as fast. And this is actually fairly acceptable, given that I actually have only 4 real cores. The hyperthreads are nice, but for expensive operations like matrix multiply, they don't actually give you a good bang as much as the real cores do. So scheduled dynamic seems to work for this example, and you can tune it. There's actually other examples that I haven't talked about. There is something called a guided, which is somewhere in between static and dynamic, but I'll leave you if you needed to learn it from the spec. So let's take a breather. I've been talking pretty. Are there any unanswered questions that require attention? I know that
I think someone in the chat asked if the parallel 4, if I remember correctly, is somewhat similar to par 4 in MATLAB. I'm not familiar with MATLAB, so I'm.
Well, I'm familiar with MATLAB, but I've never used this parallelism constructs. But you don't need to go to an analogy. Parallel 4 is very simple. It says I have a for loop that's going to execute this many times, and it's divided into threads. And we talked about how the scheduling is determined by whether it's static or dynamic, and the default is static if you don't annotate it. And you can annotate it to be dynamic. You can determine the chunk size. And further, you can learn other ways of scheduling from the spec, like guided. And there seems to be another question about collapse. Clarify, the collapse keyword makes it such that OLP attempts to split up B-square iterations. Yes, exactly. Let's come back before we run out of time. But of course, just because you put collapsed doesn't actually solve all the problems. If your two nested loops are dependent on each other, meaning the inside loop, the J on the inside loop is calculated by the outer loop's I, then that's not going to work. I'm talking about independent loops that's going to successfully collapse. But if you have actually dependent iterations, you have other issues anyway. So let's see what that might be. So here, what we're seeing here is let me get this thing. Okay. So here's the example of what we're seeing. The for loop is executing max times, and what can be an issue with this? Anyone has a guess? There's a couple of issues, I think. You want to make the iterations of each loop independent. And on the left example, what you're seeing here is the compiler cannot tell that what the J's value will be at any iteration, simply because you're kind of accessing J, you're updating it, and you're also sending it to a big function. So it actually doesn't have a lot of sense about whether the value of J will be something predictable beforehand. And you can simply remove the loop carried dependence, and that's going to help the compiler to actually safely execute the loop dependencies. So this is really saying sometimes just because you put OMP parallel 4, you might actually not get parallelism, and you have to make sure that the iteration space is correctly updated for that purpose. This is not saying anything more. Let's actually get to something, a fourth way of actually reducing computing the pi, which are reductions. Very common pattern in OpenMP. Let's say in the pi example, we don't actually even come up with an example. In the pi example, we're actually reducing the values of sum that is computed across different threads, right? The sum of different rectangles that are computed across threads, and we're trying to sum them up and find the average to calculate the area. What we can do, instead of using these critical regions or other constructs to sum the variables, we can rely on a built-in pragma compiler directive of OpenMP called reduction. So it really looks like the following. You say, what is the reduction variable? In this case, AVE, which stands for average, is my reduction variable, the variable that I'm reducing on. And what is the reduction operation, which is the plus? It can be a bunch of other things that I'm going to show in the next slide. And I just say, execute this parallel for loop, with the understanding that I am reducing over AVE. Now, you might think that there is a race condition in this code, but there isn't. Just because I annotated it correctly, the compiler understands that I'm doing a reduction on AVE, and it will somewhat automatically do what I just did. It will create a private copy for AVE for every thread, and then that value will be reduced at the exit of the loop automatically for me. So all these things that we have done, there is a shortcut for this. And the kind of things that you can, the kind of operations you can use for reductions that are predefined, you can do on plus, multiply, min, max, subtract, various bitwise operations. And these are for C++ and Fortran, they're separate, the bitwise operations. And I could use what I just learned for pi and reduce using the OMP4 reduction without worrying about the critical regions, and I would get the same correct answer. To my surprise, it seems like it's a tad bit slower, but maybe it's not worth worrying too much. I might need to rerun this thing on my modern laptop to see if the extra cost of the reduction is still there. All right. After every for loop work sharing construct, one thing you have to understand is we talked about barriers as a way to make sure that the processors synchronize with each other. It's an explicit way of synchronization across threads. But know that whenever you are executing work sharing construct, there is an implicit barrier. Like in this example, when I say OMP parallel for, no thread will go to the next line. That's, the line that's coming after the for loop before everybody completes. So there's an implicit barrier at the end of this work sharing construct. And there's implicit barriers in a lot of OpenMP constructs, and that is to make sure that you don't shoot yourself on the foot, which is a good thing. However, sometimes it can increase the runtime because of excessive synchronization that is not needed. And you see one example. So the default is to synchronize, but it allows the programmer to say that I know the next computation that I'm about to do does not require the processors to be synchronized up until that point. So you can annotate your OMP parallel for with a no wait. So let's see the examples. The first loop doesn't have no wait, so it will synchronize. And that's important because everybody is updating a different location of the C array, and that C array as a whole used for the subsequent calculation in big calculation too, right? So I need to make sure that everybody finishes updating whatever part of C that they are, so that there is no race conditions when I'm using the C here. So it's a good thing that I didn't put no wait. But in the second loop, things are different because C is effectively no variable that is involved here are going to participate in the subsequent line where I'm updating array A using just the thread ID. So it doesn't use B, it doesn't use C, it doesn't use I. So I know as a programmer that I don't need to synchronize after this loop. So I can just say no wait. And whether that is required or not, whether that's going to change your runtime, really depends on whether your threads are executing all at the same time successfully synchronously. If there's some load imbalance again across different for loops, you might want to put this no wait so that people don't always synchronize. Okay, where are we? We are 12:13. Not too bad. So far, in all our examples, we have ignored, we have, in some sense, explained what variables are shared, what variables are private. as we introduce the examples, but let's do a slightly more formal presentation of them. Of course, global variables are shared among all threads. And in fact, most variables are shared by default. This is shared memory. So however, there are ways to make things private. One is the stack variables. And every variable that is allocated within a region, within a scope region, are private too, right? So in the example we've seen, if we brought the sum inside the parallel region, it became private to each thread, and that's still the case. And in this example on the left, what we're seeing here is a index, and yes, and there's also within the function work, there is an object called count. So this is a single program you're seeing. It's not two different programs. There's this main function on the left and the work function that it calls on the right printed. So the things that are shared by all threads is the a variable that's globally defined outside the main, the index array that is defined outside the parallel region, and somewhat maybe surprisingly, the object count is also shared by all threads. And that's because it's a statically defined variable. And as you might remember, the static variables are shared across all threads. It's something that I discourage for anyone who's programming. So maybe these actual static variables make programs no longer thread safe. However, the temp variable, because it is defined inside this function work, and work is called from the parallel region, each one of these temp variables are local to the thread. Does that make sense? And that's a picture on the right. It shows how this is actually divided into processors. So these are the default ways of sharing variables, but you can annotate things, and you can say that inside this parallel region, I want these following variables to be shared, these following variables to be private. And now the surprising thing is there is something called a first private, and I will describe this. And finally, a nice thing you can do if you're into defensive programming, meaning you don't want to make mistakes, is to say default none. Because as you know, we just talked about which ones are default scoping rules about what things are shared, what things are private. You can say default none, and what that means is OpenMP, don't make default decisions. If I don't say that variable is shared or private, complain to me, and that's going to do that too. So why do I need something that's different than private? Why do I need something called the first private? It's a peculiarity, I think. Though the language designers can tell me that there's a reason for this. When you define a variable private, let's say you define temp outside the loop, and you define private, you made them private in the parallel for construct, it is actually initially uninitialized. It just becomes private, but its value is uninitialized. So that seems like a bit of a problem, as you might guess. But how you can avoid that is by calling first private, which is to say, okay, make this thing private, but also initialize it with whatever the value of the value that I'm copying from. Like incremented value 0 before the parallel region is being called. Once you say first private increment, bring that increment inside and initialize its value to 0 because that's what it was. And if you make a big C++ object, first private is going to be copy constructed, and that's the same semantics. So that's the difference. And just to recap, for understanding, is you have a bunch of variables A, B, C, and you have a parallelism constructs, OMP parallel, and you define B as private and C as first private. Since A is default shared, it will be shared by all threads, and its value will be 1 and inside the region. B and C will be private, but B will be undefined initial value. C will have its value initialized to 1 because that was the value it was set before the loop. And once the loop, the parallel region exits, B and C will revert back to their original values. Whatever changes you have done inside that parallel region will not reflect back to the variables that are outside that parallel region, except for A. If you updated A in the region, parallel region, if it is globally visible after that loop as well. And as I said, default means don't do anything. And if you don't specify shared or private of some variable, let the compiler complain to you. I have 10 minutes and only one important task to talk about. So I can take some questions that might be happening. Let me see what's going on in there in the chat. Any unanswered questions?
There's some questions about using the OpenMP parallel construct for loops that aren't iterating, that don't have integer expressions, but have other kind of expressions in the loop header. That's
a very good question, and thank you. It depends if it's as far as, and it's a flux. It's in flux in some sense, but anything the compiler can execute to somewhat of a expression that it can understand without side effects, it will do it. But if you have a list, for example, and you're iterating it in a C++ way, meaning start from the list.begin and list.end, it usually will not, because it doesn't really know whether that list can be modified during the execution. And it's much safer to just get the, if you're iterating over those objects, and if you know they're static, to get the size and just iterate using the length I. And it's somewhat changing, and I believe they might have to address this given all the iterators that are becoming more convenient. But a lot of the times you will have trouble. If you see that your compiler is complaining because you try to parallelize a loop that kind of looks like for each v in vector x, try to bring it to the old school of C++ 98, where you're iterating over I equals 0, I less than the size of the vector, and that's gonna do it for you with no problems. The short answer is your mileage might vary. Sorry. So let's get to one very exciting field in my last 8 minutes, which are tasks. Right. So this is something that is somewhat of a recent addition to OpenMP. When I say recent, I'm talking about 10 years. And tasks are essentially independent units of work, and they give you code to execute and data to compute with. Think of them as functions, a different function, and you fire up that task and say that, okay, this can compute somewhat independently, and it can execute immediately if you want. And if you have such independently executing task, you can convert your program that serially takes this long from this line on the left you see in the serial, pink, green, and purple, into something that's much faster, right? And unfortunately, OpenMP doesn't make it all that easy, because this is somewhat of an afterthought to OpenMP. OpenMP started with loops, and tasks have been introduced later. So first you need to understand this concept called a single. A single means it only makes sense within a parallel region. Once you are inside a parallel region, you can say single, and that means only one thread will execute. This is not like critical. Critical means everybody will execute that line. It's just they're not going to do it at the same time. Single means only one execution of that line will happen. It doesn't say which thread will do it. If you really wanted one thread to do it, you could call it master, but it's somewhat redundant and probably politically incorrect these days. and single means only one. So why am I telling this? Because that seems to be the only way to create tasks. Instead of easily saying create the task, the way you have to talk to OpenMP is you have to create a parallel region, because unless you create a parallel region, there is no parallelism in OpenMP. That is the only way to get parallelism, is to have some sort of OMP parallel. And once you do that, since you're going to start firing up tasks from a single source of the task tree, you have to also say, now give me a single execution of this. This seems all redundant, but unfortunately, this is the only way it works, and I verified it. And then you can start up your tasks like Fred and Daisy and Billy, and assuming they're all independent, these things are gonna execute all concurrently, in theory at least, if you have enough threads to execute them concurrently. All good. And how do you synchronize these tasks? Well, all the work sharing constructs and parallelism constructs has implicit barriers, so don't forget. At the end of the single, there will be a task wait automatically. So there is an implicit barrier right here, all tasks complete before the barrier is released. However, you can explicitly insert things if let's say you need the updates that Daisy has done or Fred has done, and it's needed by the function Billy. What you can of course do is insert an explicit synchronization construct, which is known as task wait, and it will wait until all the tasks and their children has finished by the time you get there. Okay, that's good. And am I correct on that thing? Yes, I hope so. So that's the task wait. And I'm not going to talk about data scoping rules, which gets really complicated with tasks. And my suggestion is to keep it simple with your variables and keep things private, and you'll have less of a pain, because the tasking and scoping rules are quite complicated, and you can certainly read about them. There are some nice parts of it. When the task is constructed, if variable is private, then OpenMP somehow did a good thing of initializing it for you that upgrades it by default, but I find it somewhat of a problematic feature because you don't actually know this until you read all the fine details. So let's go to an example, this old school example of computing Fibonacci in the worst possible way, which is this recursive implementation. And obviously, this just follows through the formula fn equals fn minus 1 plus fn minus 2. And nobody will implement it this way, but it's a great example for describing tasks. And this is the code to do it. How would you parallelize this? Immediately you will understand that Fibonacci n minus 1 and Fibonacci n minus 2 can be computed independently from each other. So you can fire up a task for these. And I can fire up a task for these. Of course, before I sum them up, I need the results. So I need the fib n minus 1 to finish and fib n minus 1 to finish before I can sum them up to return the value to the caller function. And for that, I use the task wait. No problem. One thing you have to realize, if you run this code or any nested code, because this is going to recursively create tasks. When you create any nested code, if you look at your task manager, which is like what I did, and don't see more than 2 threads, despite having 8 threads available running, you might wonder what's wrong with your code. But it might just be that your default OpenMP runtime is designed to turn off nested parallelism, which was the case with me and anything I have tested. So the way to fix it is to either in the code, there is a function for setting maximum active levels, or there is a environmental variable that is setting it to something larger than 1. That will create nested parallelism. So when the Fibonacci task that is being created from the task from a parallel region also creates its own descendants, the runtime will actually create more than 2 tasks. They will recursively create tasks. You have to control this thing, active levels, manually. And I find it a little obscure that you have to do it yourself, but that's how it works. And it will create this kind of task tree, and it will recursively pull back all the results, sum them up, and do what you expect it to do. So it's kind of really nice. And that's a good place to stop for our lecture. There is only two things that I didn't talk about, which are not that important because there's concepts called the atomic variables. However, many languages like C++ already have atomic in the standard library. You might actually be better off using those instead of doing it with OpenMP. It's up to you. It's essentially updating variables using the hardware primitives of atomic updates, which is usually more efficient than using critical regions that we talked about, and the semantics of the flush, which I hope you will never need to learn, because a lot of the times OpenMP will do the right thing for you. And if you have to explicitly flush things, my recommendation is to look at the program and see if you really need to do this, or you can write it in a better way that doesn't require you to manually flush things. So that's all. What's the takeaway? Programming shared memory machines seems convenient and potentially good in terms of memory consumption than creating processes, one for each core, one for processing element. However, you have to be sufficiently careful with sharing, both true sharing of data and false sharing of data, as we talked about. You have to understand that there is a memory hierarchy and there's caches when this is happening. And you have to worry about the data races and make sure that your programs do not write to a data point where multiple other threads might be writing or reading at the same time. And many of the OpenMP constructs will automatically handle some of those barriers for you, but it will not make your program trace-free. You have to think about those. And lastly, you might want to know that OpenMP is not the only thing out there. It's by and large the most popular concurrency platform for shared memory, and it's trying to expand to other areas like GPUs and accelerators in general. But we touched POSIX, pthreads. There is Intel TBB, which is a really nice library, threading library. However, know that it's also attached to a company, and it might may or may not run the same way in other processors. Silk was initially from MIT, then became a company, and then acquired by Intel and brought back to open source. Is a language that is very clean, will probably print in a cheat sheet of all the constructs, unlike OpenMP, and does effectively nested parallelism by default, and gives you some convenience functions for loop level parallelism that is converting your loop level parallelism into nested parallelism on the background. And those are your options. There might be a couple more. You can learn a lot more from tutorials that Tim Mattson, whose slides I generously used today, have been running. You can find many of his tutorials if you have the time on YouTube. And NERSC has been running training programs. I don't know if they're doing it anymore. They did it several times in the last few years. And C++ finally is extensions for parallelism, for shared memory parallelism. And with that, I believe I'm gonna stop recording and hope that it's gonna convert to something that's gonna look good.